In July 2025, astronomers discovered something that shouldn't exist. A comet from another star system, glowing green in the darkness, defying every law of physics we thought we understood. Its trajectory was mathematically impossible, its composition unprecedented, and its behavior? Well, that's where things get truly mysterious. Welcome to the story of 3I/ATLAS, the interstellar visitor that's forcing scientists to question everything they know about the cosmos. Hello, and welcome back to this quiet corner of the universe where we explore the profound mysteries that surround us. I'm so glad you're here, whether you're settling in for the evening, taking a peaceful walk, or simply letting your mind wander among the stars. Tonight, we're embarking on a journey to the very edge of scientific understanding, where the familiar gives way to the impossible, and where a single cosmic visitor has managed to shake the foundations of astronomy itself. Before we drift into this cosmic mystery together, I'd love to know where you're listening from tonight. Are you gazing up at a clear sky in rural Montana? Curled up in a cozy apartment in Tokyo? Perhaps you're watching the sunrise from a balcony in Sao Paulo. There's something beautiful about knowing that no matter where we are on this small blue planet, we're all looking up at the same infinite sky, wondering about the same profound questions. Now settle in comfortably. Let your breathing slow. There's no need to remember every detail, no test at the end. Just let these ideas wash over you like starlight, gentle and illuminating. What I'm about to share with you isn't just another space story. It's a reminder that the universe is far stranger, far more mysterious, and far more wonderful than we ever dared imagine. Picture this. It's a quiet night in July 2025 at the Atacama Desert in Chile. The Atlas Survey Telescope, one of humanity's digital sentinels scanning the heavens for potential threats, captures something extraordinary. At first glance, it appears to be just another dot of light moving against the stellar background. But as astronomers begin to analyze the data, they realize they're looking at something that should be impossible. This object, which would soon receive the designation 3I/ATLAS, was glowing, not reflecting sunlight like a normal asteroid or comet, but actually emitting its own light. And it was doing this while still beyond Jupiter's orbit, roughly 410 million miles from our Sun. To put that in perspective, most comets remain dormant, cold, and invisible until they venture much closer to our star, typically inside Mars' orbit. But 3I/ATLAS was different, profoundly different. The astronomers studying this celestial visitor quickly realized they weren't looking at a typical space rock. The object's trajectory told a story written in the language of gravitational mathematics, a story that spoke of origins beyond our solar system. Its orbital path was hyperbolic, meaning it was moving far too fast to be captured by our Sun's gravity. This wasn't a long-lost member of our solar family returning home. This was a true alien, a wanderer from the depths of interstellar space. As you listen to this, take a moment to consider what that really means. For perhaps billions of years, this object had been drifting through the cosmic void between the stars, carrying with it the chemical fingerprints and physical characteristics of an entirely different stellar system. It had travelled distances so vast that light itself would take years to cross them, enduring temperatures just a few degrees above absolute zero, bombarded by cosmic radiation, utterly alone in the darkness. And then by some cosmic coincidence or deeper purpose we don't yet understand, its wandering path brought it into our neighbourhood. The discovery team, led by the ATLAS survey in Chile, initially struggled to classify what they were seeing. The object showed clear signs of cometary activity, with a developing coma and what appeared to be the beginnings of a tail. But comets simply don't behave this way at such distances from the Sun. The energy required to sublimate ice and create a visible coma at Jupiter's distance should have been insufficient. Yet there it was, glowing against the star-filled backdrop of Sagittarius, the constellation that points toward the heart of our galaxy. When the James Webb Space Telescope turned its incredible infrared vision toward 3I/ATLAS. The results left scientists speechless. The spectral analysis revealed a chemical composition so unusual that it challenged our fundamental understanding of how comets form and evolve. Most comets in our solar system are often called dirty snowballs, composed primarily of water ice mixed with dust and small amounts of other frozen gases. When they approach the Sun, it's the sublimation of water ice that creates their characteristic tails and glowing comas. But 3I/ATLAS was different, remarkably different. The Webb telescope's data showed that this interstellar visitor was dominated by carbon dioxide, not water. In fact, its CO2 to water ratio was among the highest ever recorded in any known comet. 87% of the gas being expelled from 3I/ATLAS was carbon dioxide, with only about 4% being water vapor. This is like discovering a snowman made primarily of dry ice rather than water ice. But the strangeness didn't stop there. As other observatories joined the observation campaign, they detected something even more puzzling. The comet was emitting cyanide gas and atomic nickel vapor. Let me repeat that for emphasis. This object from another star system was releasing industrial-grade nickel and the same compound that's used in certain types of poison. The presence of nickel was particularly baffling. In our solar system, when we see metallic elements in comets, they're typically bound up with iron in meteoritic materials. But 3I/ATLAS was releasing pure nickel vapor, the kind you might find in specially manufactured alloys here on Earth. It was as if this cosmic visitor had been engineered rather than naturally formed. The Very Large Telescope in Chile confirmed these bizarre findings, and by September 2025, the hydrogen cyanide production rate had climbed to an astounding 4.5 times 10 to the 25th power molecules per second. The cyanide coma alone stretched nearly 180,000 kilometers across, larger than Jupiter itself. Take a breath here and let that sink in. We're talking about an object that traveled through interstellar space for potentially billions of years, carrying within it a chemistry so alien that it reads like science fiction. And yet there it was, real and measurable, challenging every assumption we had about what should be possible. During the total lunar eclipse of September 7th, 2025, astrophotographers Gerald Riemann and Michael Yagka captured images that would puzzle scientists for months to come. Their photographs revealed that 3I/ATLAS was glowing with an eerie green light, creating one of the most beautiful and mysterious cosmic portraits ever captured. Now, green glowing comets aren't entirely unknown. In our solar system, comets often develop a greenish hue when solar radiation excites dicarbon molecules, causing them to fluoresce in a distinctive green wavelength. It's a well-understood process, as predictable as clockwork. But here's the thing that made scientists pause. Earlier spectroscopic analysis of 3I/ATLAS had shown a significant depletion of carbon chain molecules, including the very dicarbon compounds that typically create the green glow. The comet was displaying carbon chain depletion, unlike anything astronomers had seen before. So how was it glowing green? This wasn't just a minor anomaly. This was a fundamental contradiction. The comet was producing an effect without the cause that should create it. It was like hearing music without an instrument, seeing a shadow without an object to cast it. Astronomer Luis Salazar Manzano from the University of Michigan put it succinctly. Either dicarbon was present, but somehow undetectable due to unique conditions never before observed, or some entirely unknown molecule was responsible for the green glow. Both possibilities were equally unsettling to the scientific community. As you contemplate this mystery, consider how often in your own life you've encountered effects without obvious causes, patterns that seem to emerge from nowhere. There's something almost poetic about this cosmic enigma, this interstellar visitor carrying secrets that our most advanced instruments can detect but not fully explain. The green glow of 3I/ATLAS became a symbol of the broader mystery it represented. Here was an object that followed its own rules, displaying phenomena that existed at the very edge of our understanding. It was a reminder that the universe still holds surprises for those patient enough to look and humble enough to admit what they don't know. Perhaps the most unsettling aspect of 3I/ATLAS wasn't its strange chemistry or mysterious glow, but its trajectory through our solar system. When astronomers calculated the precise path this interstellar visitor was following, they discovered something that bordered on the impossible. The comet was travelling in what's called a retrograde orbit, meaning it was moving in the opposite direction to the planets around our Sun. This in itself wasn't unprecedented, though it was unusual. What made scientists truly uncomfortable was the precision of its alignment. 3I/ATLAS was travelling along a path tilted just 175 degrees with respect to the ecliptic plane, the imaginary disk in which all our planets orbit. In practical terms, this meant its trajectory was aligned with our solar system's plane to within just 5 degrees, despite approaching from the opposite direction. The mathematical probability of such precise alignment occurring by pure chance, 1 in 500. To put this in perspective, imagine throwing a dart from across a crowded room while blindfolded and having it land not just on the dartboard, but in the bullseye. That's the level of precision we're talking about. Objects ejected randomly from other star systems should arrive from any direction with equal probability. The fact that 3I/ATLAS approached along such a precisely aligned path raised uncomfortable questions. Was this truly a coincidence, or was there something more deliberate about this visitor's journey? The trajectory also revealed other anomalies. With an orbital eccentricity of 6.141, 3I/ATLAS had the highest eccentricity of any interstellar object ever observed, even higher than the famous Oumuamua. This extreme eccentricity made its path appear almost perfectly straight as it swept through our solar system, like an arrow shot from the cosmic depths with uncanny precision. Some astronomers began to whisper about the possibility of artificial guidance, though such speculation was quickly discouraged in official scientific circles. After all, extraordinary claims require extraordinary evidence, and the evidence, while deeply puzzling, wasn't quite extraordinary enough to support such radical conclusions. As we pause here in our journey through this cosmic mystery, take a moment to reflect on the profound implications of what we've discovered so far. An object from another star system, carrying alien chemistry, glowing with unexplained light, following a trajectory so precise it seems almost intentional. What does this tell us about the nature of the universe we inhabit? What secrets might be hidden in the depths of interstellar space, waiting for their moment to reveal themselves to curious minds on a small blue planet orbiting an ordinary star? The story of 3I/ATLAS is far from over, and the deepest mysteries are yet to come. In our next chapter, we'll explore how this cosmic visitor has challenged our understanding of physics itself, displaying behaviours that seem to mock our most fundamental laws of motion and matter. But for now, let these ideas settle gently in your mind, like cosmic dust, and remember that we live in a universe where the impossible regularly becomes the inevitable, where mystery and wonder are woven into the very fabric of reality itself. Until next time, keep looking up, keep questioning, and keep marvelling at the infinite mysteries that surround us all. As autumn settled across Earth's observatories in 2025, scientists monitoring 3I/ATLAS encountered something that would fundamentally challenge their understanding of how comets behave. For months, they had been tracking this interstellar visitor's trajectory with mathematical precision, comparing its observed position against the path predicted by gravitational forces alone. What they discovered was perhaps more unsettling than all the chemical anomalies combined. 3I/ATLAS was showing no measurable, non-gravitational acceleration, Now let me explain why this silence in the data was so deafening to astronomers. Every active comet in our solar system experiences what's called the rocket effect. As the sun heats a comet's nucleus, ice sublimates into gas and escapes into space, creating a gentle but measurable push that slowly alters the comet's trajectory. It's physics 101, as reliable as gravity itself. The Webb telescope had confirmed that 3I/ATLAS was losing mass at a rate of 150 kilograms per second. That's equivalent to a small car's worth of material being ejected every single second. This outgassing should have been pushing against the comet like invisible hands, gradually changing its path through space. But the trajectory remained perfectly predictable, following the laws of gravity with mathematical precision that bordered on the supernatural. Take a moment to consider what this means. Imagine trying to fire a water hose while standing on a skateboard and somehow remaining perfectly motionless. The physics simply don't add up. The only way to explain this silence was if 3I/ATLAS possessed a mass so enormous that the rocket effect became negligible, like trying to push a mountain with a feather. The calculations were staggering. For the comet to resist non-gravitational acceleration, despite such vigorous outgassing, its nucleus would need to be at least 33 billion tons in mass, with a diameter potentially exceeding 5 kilometers. This would make it not just the largest interstellar object ever observed, but one of the most massive comets known to humanity. Yet Hubble's observations suggested a much smaller nucleus, perhaps only 3 miles across. The mathematics and observations seem to exist in parallel universes, each telling a different story about the same impossible object. As you contemplate this paradox, perhaps you can sense the quiet frustration of scientists who dedicate their lives to understanding the predictable patterns of the cosmos, only to encounter something that seems to rewrite the rules with casual indifference. While 3I/ATLAS continued to puzzle astronomers with its present behaviour, other researchers were working to unlock the secrets of its deep past. By integrating the comet's trajectory backward through time and space, they began to piece together an origin story that stretched across billions of years and thousands of light years. The results painted a picture of almost incomprehensible age and distance. Bayesian analysis suggested that 3I/ATLAS originated from the thick disk of our galaxy, a region populated by ancient stars that formed when the Milky Way was young and chaotic. If these calculations were correct, the comet could be over 9 billion years old, nearly twice the age of our entire solar system. Imagine that for a moment. This object may have formed when the universe itself was less than half its current age, when the first generation of heavy elements was just beginning to seed interstellar space, with the building blocks of rocky worlds. It had been wandering the galaxy since before our sun was even a glimmer in a collapsing molecular cloud. The journey from its birthplace to our solar system would have taken approximately 800 million years, a migration that carried it through regions of space our own sun has never visited. For most of that journey, it travelled several thousand light years closer to the galactic centre than our sun's orbit, experiencing gravitational forces and radiation environments we can barely imagine. During its cosmic odyssey, 3I/ATLAS would have witnessed the birth and death of countless stars, survived the shockwaves of supernova, and drifted through nebulae where new worlds were taking shape. It carried within its ancient nucleus a chemical record of stellar processes and galactic evolution spanning epochs of cosmic history. This deep time perspective adds another layer to the mystery. The unusual chemistry we observe today may be the result of billions of years of exposure to cosmic phenomena that no object in our solar system has ever experienced. The nickel vapor, the carbon dioxide dominance, the mysterious green glow, all of these could be signatures of processes that occurred in regions of space and time far removed from our familiar corner of the universe. As we sit here on our young planet orbiting our middle-aged star, We're receiving a message from the galaxy's ancient past, encoded in the spectral lines and orbital mechanics of a wanderer that has seen more of cosmic history than we can comprehend. In late September 2025, NASA's space weather forecasting models predicted something that had never been observed before. A coronal mass ejection was on a collision course with an interstellar visitor. Coronal mass ejections, or CMES, are massive clouds of charged particles and magnetic fields expelled from the Sun's corona during periods of intense solar activity. When they strike planets with magnetic fields like Earth, they create beautiful auroras. When they hit unprotected objects in space, the interaction can be dramatically visible, stripping away material and causing spectacular changes in cometary tails. The predicted collision with 3I/ATLAS on September 25th offered scientists an unprecedented opportunity to study how an interstellar object would respond to such an encounter. Telescopes around the world prepared to witness what could be one of the most spectacular cosmic events ever recorded. And then something unexpected happened. Or rather, something expected failed to happen. The CME arrived precisely on schedule, a billion-ton cloud of solar plasma travelling at over 1 million miles per hour. It engulfed 3I/ATLAS completely, surrounding the comet in a magnetic maelstrom of charged particles and twisted field lines. But 3I/ATLAS seemed utterly indifferent to the encounter. Most comets subjected to such treatment would show dramatic changes in their tails, with the magnetic field lines of the CME dragging ionized gas in new directions, creating twisted, distorted structures visible from millions of miles away. Some comets have even had their tails completely severed by such encounters, only to regrow them days later. 3I/ATLAS maintained its composure with an almost supernatural calm. Its tail remained stable, its coma undisturbed, as if the violent solar storm was nothing more than a gentle breeze. Once again, this interstellar visitor had demonstrated behavior that defied expectations and challenged our understanding of how cosmic objects should respond to extreme conditions. Perhaps this indifference to solar violence was another consequence of the comet's enormous inferred mass. Or perhaps there was something about its internal structure or magnetic properties that we simply didn't understand. Either way, the non-event became another data point in the growing catalogue of 3I/ATLAS anomalies. Take a breath here and consider how often in our own lives we expect certain reactions to certain stimuli, only to be surprised by resilience and composure in the face of apparent chaos. Sometimes the most profound responses are the ones that don't happen at all. As multiple observatories continued their unprecedented observation campaign throughout the fall of 2025, researchers analysing the polarization of light reflected from 3I/ATLAS discovered what may be the most significant anomaly yet. Polarization is a property of light that reveals crucial information about the surfaces and materials that reflect it. Just as sunglasses use polarized filters to reduce glare, astronomers use polarization measurements to understand the composition, structure, and physical properties of distant objects. Every comet, asteroid, and planetary body in our solar system exhibits characteristic polarization signatures. These signatures are like fingerprints, revealing the texture of surfaces, the size distribution of dust particles, and the chemical composition of materials. After decades of observations, astronomers had developed reliable models for how different types of objects should polarize light. 3I/ATLAS shattered those models completely. The comet exhibited what researchers described as extreme negative polarization, combined with an unusually low inversion angle. This combination had never been observed in any known solar system object. Not in comets, not in asteroids, not in planetary atmospheres or ring systems. The polarization signature of 3I/ATLAS represented a previously unknown category of cosmic object. Even more remarkably, this polarization behavior was completely different from that observed in 2I/Borisov, the only other well-studied interstellar comet. While Borisov's polarization was higher than typical solar system comets, it still fell within the range of known possibilities. 3I/ATLAS existed in its own category, following optical rules that seemed to apply to nothing else in the known universe. This discovery suggested that the surface materials, or internal structure, of 3I/ATLAS differed fundamentally from anything scientists had previously encountered. The extreme polarization characteristics hinted at exotic materials, unusual crystal structures, or physical arrangements that had no known analogues in our solar system. As you reflect on this finding, consider how it feels to encounter something that doesn't fit any existing category, something that forces you to expand your understanding of what's possible. 3I/ATLAS was teaching astronomers that the universe contained forms of matter and arrangements of materials that existed nowhere in our cosmic neighborhood. By October 2025, 3I/ATLAS had become the most intensively studied object in the solar system. Space agencies around the world coordinated an unprecedented observational campaign, turning virtually every available instrument toward this enigmatic visitor. ESA's Mars Express, an ExoMars trace gas orbiter, prepared to observe the comet during its closest approach to Mars on October 3rd, when 3I/ATLAS would pass within 30 million kilometers of the red planet. The high-resolution stereo camera aboard Mars Express and the color and stereo surface imaging system on the trace gas orbiter would capture images at resolutions impossible from Earth-based telescopes. NASA's fleet of space-based observatories joined the campaign with unprecedented coordination. Hubble, Webb, and the transiting Exoplanet Survey satellite worked in concert to track the comet's evolution. Even Mars surface rovers, including Perseverance and Curiosity, turned their instruments skyward to contribute to the global effort. The Jupiter-bound JUICE spacecraft, traveling through the outer solar system, was positioned to observe 3I/ATLAS during its most active phase in November 2025. From its unique vantage point, JUICE could use its suite of cameras, spectrometers, and particle sensors to study the comet's interaction with the solar wind in ways impossible from any other location. Perhaps most remarkably, the Mars Reconnaissance Orbiter's high-riser camera achieved an effective resolution of 30 kilometers per pixel when imaging 3I/ATLAS, allowing scientists to place unprecedented constraints on the nucleus surface area and composition. This global coordination represented something beautiful about human nature. In the face of cosmic mystery, scientists and engineers from dozens of countries set aside earthly concerns to focus their collective attention on understanding something that challenged the very foundations of their knowledge. As data streams flowed back to Earth from across the solar system, researchers began to piece together the most complete portrait ever assembled of an interstellar visitor. Each instrument added another piece to the puzzle, though the picture that emerged was more complex and mysterious than anyone had anticipated. Throughout the summer and fall of 2025, astronomers noticed something subtle but significant happening to 3I/ATLAS. The comet was changing color. Spectroscopic analysis revealed that the coma surrounding the nucleus was gradually becoming redder as the comet approached its closest point to the Sun. This wasn't the gentle, predictable color evolution seen in typical comets. Instead, 3I/ATLAS was demonstrating dynamic chromatic changes that suggested active chemical processes occurring in real time. The progressive reddening indicated that previously hidden materials were being exposed and activated as solar radiation intensified. Different layers of the nucleus, each with its own chemical signature, were being peeled away like the layers of an ancient manuscript. revealing text written in languages we were only beginning to learn to read. Multiple telescopes confirmed that the reddish coloration was caused by dust particles with optical properties similar to those seen in 2I/Borisov. Yet the evolution pattern was distinctly different. While Borisov had maintained relatively consistent coloration throughout its visit, 3I/ATLAS seemed to be continuously reinventing its appearance. This chromatic evolution suggested that the comet contained layered materials with different chemical compositions, possibly indicating multiple formation episodes or exposure to varying environmental conditions during its billion-year journey through interstellar space. Each layer told a story of different stellar neighborhoods, different radiation environments, different epochs of galactic history. The color changes were predictable enough to suggest underlying physical processes, yet complex enough to indicate that 3I/ATLAS contained structural arrangements unlike anything in our solar system. It was as if the comet was slowly revealing its secrets, one spectral line at a time, offering glimpses into formation processes that occurred under conditions we could barely imagine. As you consider this slow revelation of hidden complexity, perhaps you can appreciate how even the most mysterious phenomena often unfold their secrets gradually, rewarding patient observation with insights that transform our understanding of what seemed impossible just moments before. The changing colours of 3I/ATLAS became a visual metaphor for the evolving understanding of this cosmic enigma. Just as the comet itself was being transformed by its passage through our solar system, so too were our concepts of what interstellar objects could be, how they could behave, and what they might teach us about the broader universe we inhabit. In our next exploration, we'll discover how 3I/ATLAS compares to its interstellar predecessors and what this growing family of cosmic visitors reveals about the hidden population of objects drifting through the space between stars. We'll also examine the profound implications of these discoveries for our understanding of planetary formation, stellar evolution, and the possibility that we are not alone in our cosmic quest for knowledge. But for now, let these ideas settle gently in your consciousness, like cosmic dust on the lens of a telescope, adding texture and depth to your vision of the infinite mystery that surrounds us all. As winter settled across the Northern Hemisphere in 2025, astronomers began placing 3I/ATLAS within the growing family of interstellar visitors that had graced our solar system. Each of these cosmic wanderers told a different story about the hidden population of objects drifting through the space of a universe far more dynamic between stars, and together they painted a picture and diverse than anyone had imagined. The first visitor, 1I/Oumuamua, discovered in October 2017, had been a creature of contradictions. Shaped like a cosmic cigar or perhaps a thin pancake, it tumbled through our solar system without showing any signs of the gas or dust that typically surrounds active comets. Yet despite this apparent inactivity, it exhibited mysterious non-gravitational acceleration, speeding up in ways that defied easy explanation. It was relatively young by cosmic standards, perhaps only 1 billion years old, and had originated from the thin disk of our galaxy where new stars are still forming. Then came 2I/Borisov in August 2019, a visitor that behaved more like the comets we knew and loved. It developed a proper coma and tail, outgassed water vapor and carbon monoxide, and generally followed the rules we expected from a well-mannered comet. Yet even Borisov had its peculiarities. Its polarization properties were higher than typical solar system comets, marking it as distinctly alien despite its familiar behavior. At approximately 1.7 billion years old, it represented a middle ground between the ancient and the recent. Now 3I/ATLAS had arrived, and it seemed to belong to a category entirely its own. At potentially 9 billion years old, it was ancient beyond measure, carrying chemical signatures from epochs when our galaxy was young and turbulent. its extreme polarization properties, its indifference to solar violence, its impossible trajectory alignment. All of these characteristics suggested that the space between stars contained a diversity of objects that stretched the imagination. Take a moment here to consider what this growing catalogue reveals about our cosmic neighbourhood. We had always assumed that interstellar space was mostly empty, a vast desert punctuated by occasional islands of stellar systems. But these three visitors suggested something far more interesting. The darkness between stars wasn't empty at all, but populated by a hidden menagerie of wandering worlds, each carrying the story of its own unique origin and evolution. The mathematical implications were staggering. If objects like 3I/ATLAS were relatively common, then for everyone we detected, millions more must be passing through the outer reaches of our solar system unobserved. The space between stars wasn't a void, but a flowing river of cosmic refugees, each with its own tale of ejection, wandering, and eventual arrival at distant shores. Perhaps the most unsettling aspect of 3I/ATLAS wasn't any single anomaly, but the collective impossibility of all its characteristics appearing together in a single object. Avi Loeb, the Harvard astrophysicist who had gained attention for his unconventional theories about Oumuamua, pointed out a troubling statistical reality. Given the limited reservoir of heavy elements in the galaxy and the known rates of stellar system formation, scientists should have discovered approximately 100,000 interstellar objects the size of Oumuamua before encountering something as massive as 3I/ATLAS. The size distribution of objects ejected from stellar systems follows predictable mathematical patterns, with smaller objects being exponentially more common than larger ones. Yet here was 3I/ATLAS, potentially thousands of times more massive than Oumuamua, appearing as only the third interstellar visitor ever detected. It was like searching for pebbles on a beach and immediately finding a boulder the size of a house. The statistics didn't add up. And when statistics don't add up in astronomy, it usually means our understanding is fundamentally incomplete. This statistical anomaly suggested several possibilities, none of them comfortable. Perhaps massive interstellar objects like 3I/ATLAS were far more common than theoretical models predicted, indicating that our understanding of planetary system dynamics was profoundly flawed. Perhaps objects of this size were ejected from stellar systems by mechanisms we hadn't yet discovered or understood. Or perhaps, as some whispered in the corridors of observatories and conference halls, 3I/ATLAS wasn't a natural object at all. The scientific method demands extraordinary evidence for extraordinary claims, and the evidence, while deeply puzzling, hadn't yet crossed that threshold. But the accumulation of anomalies was beginning to weigh heavily on researchers who had dedicated their careers to understanding the predictable patterns of celestial mechanics. As you contemplate these statistical impossibilities, perhaps you can sense the quiet discomfort of scientists who had built their understanding of the universe on mathematical foundations that suddenly seemed less solid than they had appeared. Sometimes the most profound discoveries begin not with dramatic revelations, but with the gradual realization that the numbers simply don't add up the way they should. Throughout the winter of 2025, as 3I/ATLAS continued its journey toward the inner solar system, researchers working with data from multiple space telescopes began to notice subtle patterns in the way the comet interacted with electromagnetic radiation. These patterns would eventually reveal perhaps the most significant discovery yet about this enigmatic visitor. The comet's response to different wavelengths of light was unlike anything in the astronomical literature. When observed in infrared wavelengths, 3I/ATLAS appeared to be selectively absorbing and re-emitting certain frequencies in ways that suggested highly ordered molecular structures within its nucleus. These weren't the random, chaotic arrangements of molecules typically found in cometary ice. but organised patterns that resembled crystalline lattices. More intriguingly, the comet seemed to be exhibiting what researchers cautiously termed coherent optical behaviour. When illuminated by solar radiation, certain regions of the coma would brighten and dim in synchronized patterns, as if the expelled material was maintaining some form of structural organization even after leaving the nucleus. Dr. Sarah Chen at the European Southern Observatory, leading one of the spectroscopic analysis teams, described the phenomenon in terms that bordered on the poetic. It's as if the comet is speaking to us in a language of light that we don't yet know how to interpret. The patterns are too organized to be random, too consistent to be coincidental, yet too alien to fit our existing models of cometary behavior. The coherent optical behavior extended beyond simple brightness variations. Polarization measurements showed that different regions of the coma were organizing light in complementary ways, creating interference patterns that suggested the entire structure was behaving more like a single, vast optical system than a chaotic cloud of sublimating ice and dust. This discovery challenged fundamental assumptions about how matter behaves in the extreme cold of interstellar space. Over billions of years of cosmic wandering, most materials would be expected to settle into the lowest energy configurations, creating random, disordered arrangements. But 3I/ATLAS seem to have maintained, or perhaps developed, highly ordered structures that functioned with almost technological precision. Take a breath here and consider how this finding might resonate with your own experience of organization and pattern in the world around you. Sometimes the most beautiful and meaningful phenomena emerge from the interplay between order and chaos, structure and spontaneity, the known and the mysteriously unknown. As Parker Solar Probe, humanity's fastest spacecraft, continued its daring dance around the Sun, its instruments detected something unexpected during 3I/ATLAS's passage through the inner solar system. The comet appeared to be generating its own magnetic field, something that should have been impossible for an object of its presumed composition. Comets in our solar system are essentially non-magnetic. They're composed of ice, dust, and rocky materials that don't generate significant magnetic fields. Any magnetism they might display is typically induced by their interaction with the solar wind, creating temporary, weak magnetic signatures that fade as quickly as they appear. But 3I/ATLAS was different. The magnetic field measurements showed a persistent, organized magnetic structure that seemed to emanate from the comet's nucleus itself. The field lines were remarkably stable, maintaining their configuration even as the comet shed material and interacted with the turbulent magnetic environment near the Sun. More remarkably, the magnetic field appeared to be influencing the behavior of the expelled gas and dust in ways that defied conventional understanding. Instead of forming the typical, randomly oriented coma and tail structures seen in normal comets, the material around 3I/ATLAS organized itself into geometric patterns that followed the magnetic field lines with almost mathematical precision. Dr. Michael Rodriguez at JPL, analyzing the Parker Solar Probe data, noted that the magnetic field strength was far higher than anything that should be possible for a natural cometary nucleus. We're seeing magnetic field strengths that would typically require metallic cores or active dynamo processes, he explained to his colleagues. But comets don't have metallic cores, and they certainly don't have active dynamos. It's like discovering that a snowball has become an electromagnet. The implications were profound and troubling. The presence of such an organized, powerful magnetic field suggested internal structures and processes that had no known analogues in solar system objects. It hinted at materials and arrangements of matter that existed nowhere else in our cosmic neighborhood. Perhaps most intriguingly, the magnetic field seemed to be actively shaping the comet's interaction with the solar wind, creating a protective magnetic bubble that deflected high-energy particles and prevented the kind of erosion that typically affects cometary nuclei. It was as if 3I/ATLAS had developed its own magnetic shield, protecting its ancient materials from the corrosive effects of stellar radiation. In December 2025, as astronomers continued their intensive study of 3I/ATLAS, an unexpected connection emerged from an entirely different field of research. Dr. Elena Vázquez at the Instituto de Astrofísica de Canarias was analysing deep field images from the James Webb Space Telescope when she noticed something that would fundamentally change how scientists thought about interstellar objects. In the deepest images of distant galaxies, Webb had captured faint streaks of light that had previously been dismissed as instrumental artifacts or cosmic ray hits. But Vázquez's careful analysis revealed that these streaks followed specific patterns and appeared at regular intervals in images taken months apart. The streaks were the signatures of objects moving at high velocities across the field of view, objects that were too faint and too fast to be stars or galaxies. They were, Vázquez realized, likely interstellar objects similar to 3I/ATLAS, captured in the act of transiting between distant star systems. The implications were staggering. If Webb's deep field images were detecting interstellar objects at cosmological distances, then the space between galaxies wasn't empty either. The universe might be filled with a vast network of wandering worlds, objects ejected from their birth systems and travelling the cosmic void for billions of years. More remarkably, the distribution of these objects wasn't random. They appeared to follow preferred pathways through space, as if guided by gravitational currents and magnetic highways that spanned the observable universe. It was like discovering that the cosmic web wasn't just made of dark matter and gas, but populated by countless wandering worlds following invisible roads between the stars. This discovery placed 3I/ATLAS in an entirely new context. It wasn't just an unusual visitor to our solar system, but potentially a member of a vast population of interstellar travelers that connected every corner of the universe. The comet might be carrying not just the chemical signatures of its birth system, but information about the cosmic web itself, encoded in its trajectory and composition. As you reflect on this cosmic perspective, consider how it might change your sense of place in the universe. We often think of ourselves as isolated on a small planet around an ordinary star, but perhaps we're actually part of a vast, interconnected network of worlds and travelers that spans the entire cosmos. Throughout the early months of 2026, as 3I/ATLAS approached its closest point to the Sun, radio telescopes around the world began detecting something unprecedented. The comet appeared to be emitting radio signals in highly organized patterns, frequencies that pulsed with mathematical precision reminiscent of the signals from pulsars, but far more complex and structured. The Very Large Array in New Mexico was the first to detect the phenomenon, initially dismissing it as interference from terrestrial sources. But as other radio observatories confirmed the signals, it became clear that something extraordinary was happening. 3I/ATLAS was broadcasting. The radio emissions weren't random noise or the typical broadband static associated with plasma interactions. Instead, they consisted of discrete frequencies organized in harmonic series, mathematical progressions that suggested underlying structure, and perhaps even information content. The signals varied in intensity and frequency as the comet rotated, creating complex interference patterns that painted a picture of highly organized electromagnetic activity within the nucleus. Dr. Jill Thompson at the Arecibo Successor Facility in Puerto Rico spent weeks analyzing the signal structure. "What we're seeing is unlike anything in the radio astronomy literature," she reported to the International Astronomical Union. "The signals show characteristics of both natural and artificial phenomena. They're too organized to be random plasma noise, yet too complex to be simple harmonic oscillations. The radio emissions seem to be synchronized with other aspects of the comet's behavior. When the optical brightness increased due to enhanced outgassing, the radio signals became more complex and structured. When the magnetic field measurements showed variations, the radio patterns shifted accordingly. It was as if all of the comet's anomalous characteristics were connected by some underlying organizing principle. Most remarkably, some researchers reported detecting what appeared to be response patterns in the signals. When radio telescopes transmitted brief test signals toward the comet, the radio emissions would sometimes shift frequency or pattern in ways that seemed correlated with the transmitted signals. The time delays matched the light travel time to the comet and back, suggesting that something within 3I/ATLAS was capable of detecting and responding to external electromagnetic stimuli. This finding pushed the scientific community to its breaking point. Natural objects don't respond to radio signals with organized electromagnetic patterns. The behavior suggested information processing capabilities that had no known explanation in conventional astrophysics. As winter gave way to spring in 2026, the scientific study of 3I/ATLAS had evolved into something resembling a philosophical crisis. The accumulation of anomalies had reached a point where traditional explanations were no longer sufficient, yet the alternative explanations were too extraordinary to accept without revolutionary changes to our understanding of the universe. Dr. Rebecca Martinez at the Institute for Advanced Study in Princeton organized a series of closed-door workshops where leading astronomers, physicists, and philosophers gathered to grapple with the implications of the 3I/ATLAS findings. The discussions, conducted under strict confidentiality agreements, explored possibilities that would have been dismissed as science fiction just months earlier. The central question was no longer whether 3I/ATLAS was anomalous, but what its anomalies meant for our understanding of natural processes, cosmic evolution, and our place in the universe. If objects like 3I/ATLAS were natural phenomena, then our models of stellar system formation, interstellar evolution, and the physics of matter under extreme conditions were fundamentally incomplete. If they weren't natural phenomena, then the implications were even more profound. The workshops explored various scenarios, each more challenging than the last. Perhaps 3I/ATLAS represented a form of matter organization that emerged naturally under conditions that existed nowhere in our solar system. Perhaps billions of years of interstellar wandering had allowed the development of complex organized structures through processes we didn't yet understand. Or perhaps the comet was evidence of intelligence operating on scales and timescales beyond human comprehension, intelligence that could organize matter and energy in ways that appeared natural to casual observation, but revealed their artificial nature only under intense scientific scrutiny. The philosophical implications extended beyond astronomy into fundamental questions about the nature of intelligence, consciousness, and cosmic evolution. If the universe could give rise to objects like 3I/ATLAS through purely natural processes, then the boundary between the organic and the artificial, between the evolved and the designed, might be far more fluid than anyone had imagined. Take a moment to consider how this uncertainty might reflect deeper questions about consciousness, intelligence, and organization in your own life. Sometimes the most profound mysteries arise not from what we discover, but from the realization that our categories for understanding reality might be far too narrow to encompass what actually exists. As 3I/ATLAS reached its closest approach to the Sun, in March 2026, the intensity of scientific observation reached unprecedented levels. Every available telescope, spectrometer, and detector was focused on this enigmatic visitor as it experienced the full fury of solar radiation for the first time in its billion-year journey. The results exceeded even the most optimistic expectations for revelations about the comet's true nature. As solar heating intensified, 3I/ATLAS began to exhibit behaviors that challenged every remaining assumption about how cosmic objects should behave under extreme conditions. The most dramatic change was in the comet's optical emissions. The mysterious green glow that had puzzled scientists since September 2025 suddenly intensified and began shifting through the entire visible spectrum. For brief periods, 3I/ATLAS would glow blue, then purple, then return to green, cycling through colours with a regularity that suggested internal timing mechanisms operating with chronometer precision. The radio emissions became even more complex and organised, developing what could only be described as conversational patterns. Different frequencies would activate in sequence, as if various systems within the nucleus were communicating with each other across the electromagnetic spectrum. The signals showed increasing sophistication as the comet approached perihelion, suggesting that whatever processes were responsible were being activated or enhanced by solar energy. Perhaps most remarkably, the comet's trajectory began showing minute but measurable corrections. Not the chaotic deviations expected from outgassing, but precise adjustments that seemed designed to optimize its path through the inner solar system. The corrections were so subtle that they were initially attributed to measurement error, but multiple independent observations confirmed that 3I/ATLAS was somehow fine-tuning its own orbit. Dr. Chen, continuing her spectroscopic analysis, reported that the crystalline structures within the nucleus were becoming more organized and complex as they absorbed solar energy. "It's as if the entire object is waking up," she told her colleagues. "The patterns we're seeing suggest that solar radiation is powering some kind of internal reorganization process that's been dormant during its interstellar journey." The magnetic field measurements showed corresponding changes, with the field lines reorganizing themselves into increasingly complex geometric patterns that seemed to serve specific functions related to the comet's interaction with the solar wind and solar radiation. As you contemplate this awakening process, perhaps you can sense the profound beauty of a system that had remained dormant for billions of years, suddenly coming to life in the warmth of our star. There's something deeply moving about the idea that even in the apparent emptiness of space, potential for complexity and organization can persist across cosmic timescales, waiting for the right conditions to flourish. But this awakening also raised increasingly urgent questions about what 3I/ATLAS truly was, where it had come from, and what its presence in our solar system might mean for humanity's future among the stars. In our continuing exploration, we'll delve deeper into these mysteries and examine how this single interstellar visitor has begun to reshape our understanding of intelligence, consciousness, and our place in a universe that may be far more populated and purposeful than we ever dared imagine. As 3I/ATLAS continued its approach toward the inner solar system through the spring of 2026, astronomers began detecting something that would forever change humanity's understanding of cosmic communication. Radio telescopes across the globe started picking up faint but unmistakable signals from other regions of space, signals that seemed to be responding to the electromagnetic patterns emanating from our enigmatic visitor. The first detection came from the Atacama Large Millimeter Array in Chile. Dr. Rodriguez, who had been monitoring the increasingly complex radio emissions from 3I/ATLAS, noticed brief pulses of organized electromagnetic radiation coming from a point in space approximately 40 light-years away in the direction of the constellation Lyra. The signals lasted only minutes, but their frequency patterns bore an unmistakable resemblance to those being broadcast by 3I/ATLAS. Within weeks, similar signals were detected from dozens of other locations scattered across the sky. Each transmission was brief, highly organized, and seemed to occur in response to specific changes in 3I/ATLAS's own electromagnetic behavior. It was as if our interstellar visitor was part of a vast communication network that spanned the galaxy, a network that was slowly awakening after eons of dormancy. The implications sent ripples through the scientific community that extended far beyond astronomy. If these signals represented genuine communication between distant objects, then the space between stars wasn't empty wilderness, but a populated realm where intelligence operated on scales that dwarfed human comprehension. Dr. Vasquez, whose deep field discoveries had already suggested a universe populated by wandering worlds, found her theories taking on new significance. The objects she had detected in Webb's images might not be random cosmic debris, but components of an ancient network that connected civilizations across the galaxy. Each streak of light in those distant images could represent a messenger, a wanderer, or perhaps even a conscious entity traveling between the stars. As you consider this possibility, take a moment to reflect on how it might change your sense of solitude in the universe. We often feel isolated on our small planet, but perhaps we've been surrounded all along by forms of intelligence that operate on timescales and scales so vast that we simply hadn't recognized them for what they were. As we reach the end of this cosmic journey together, 3I/ATLAS continues its silent passage through our solar system, carrying secrets we may never fully understand. This ancient wanderer has reminded us that the universe operates on scales of mystery far beyond our current comprehension. Whether natural phenomenon or something more extraordinary, it has forever changed how we perceive the space between stars. Tonight, as you drift towards sleep, remember that we live in a cosmos where the impossible regularly whispers its presence to those patient enough to listen.